Good afternoon, Ada's Technical Books. We're starting a presentation in the back room, if you'd care to join us. This afternoon, we're fortunate to have Richard Yonck here to present on living in a connected world. Richard is a foresight analyst who writes about the future for numerous publications. He's a computing AI contributing editor for the Futurist magazine, which will soon celebrate its 50th year. Connecting with our connected world is his third cover story for them. If you'd like to join us in the back room, we'll be getting started right now. Here's Richard.
Thank you very much for coming out. I appreciate seeing so many people here in spite of the fact that we have a Doctor Who special going on today. So my name is Richard Yonck, and I write about the future. More specifically, I write about usually emerging technologies and where they'll be in 10 or 20 years' time, and how we might leverage that information to create better outcomes for ourselves as a society and as individuals. So back in the spring, I was looking at writing an article about the Internet of Things, and in doing so, I was noticing that other people had written had mostly been very, very positive. Gee whiz, look at all the amazing things we're going to be able to do with this new toy. And I thought, there's some possible negative repercussions, some things that might not necessarily go the way we want. And so I wanted to explore some of those a little bit in the course of this article. So just by a show of hands, how many people here are reasonably familiar with what the Internet of Things is? Okay. Not, I guess, surprising in a technical bookstore. So, in a nutshell, very, very simply, the Internet of Things is things connected to the Internet. It's literally as simple as that. However, where for decades we've had computers, laptops, smartphones, other devices connected, soon we're going to be having all manner of different things connected. Literally everything in our urban environment, our rural environment, our natural environment. There are going to be sensors literally everywhere. And it's going to dramatically change our world and our worldview, I think, in that time. So as we move into it, we're going to have our homes, our appliances, literally things as seemingly innocuous as our car keys, addressable via the Internet. Handy if you have a habit of losing your car keys, I suppose. But there are going to be things that we may not necessarily want to see connected in time. Now, 40% of Internet traffic, based on an IDC 2012 report, is machine-to-machine communication. This is up from 2005, when about 11% was machine-to-machine. And this trend is only going to progress, is only going to grow to a much, much larger percentage of the traffic. And in many respects, this is a good thing, because it's going to be happening so fast. The communication is so rapid, the data is so vast, that there's really no way for human beings to have a direct interaction, direct way of communicating and overseeing this. And yet, if that's the case, at the same time, we have to do some things to make sure that we have adequate oversight, adequate control of how this data is used, what it does, and what its relationship is to us. So, the big question is why now? Why is the Internet of Things happening at this time rather than 10 years ago, 20 years ago? And there's a few different reasons for that. One of the main things is money. This is going to be a very, very big money activity for a lot of businesses. You're going to see a huge amount of money invested. You're going to see a huge amount of money made. Now, in the 2012 white paper, Cisco estimated that over the next 10 years, the Internet of Things is going to amount to $4.4 trillion. That's obviously a very significant amount of money. Not to be outdone, GE estimates that over the next 20 years, what they're calling the industrial internet, which for the most part overlaps with the Internet of Things, is going to amount to $15 trillion. Now, just to put this in perspective, this is approximately the entire annual GDP of the United States. So it's a huge amount of money that these people are chasing, and they're going to continue to do so. The next thing that is a big factor that's driving this is our old friend Moore's Law. Now, many of you, I'm sure, are familiar with the paper in 1965 that Gordon Moore of Intel published, in which he plotted 4 data points of prior years of transistor density on semiconductor chips at Intel. And in looking at the regular doubling that was occurring on a regular basis, approximately every 2 years at that time, he determined, he thought that this trend would continue for another decade or so. Well, it's gone on for a lot longer than that. It's gone on for approximately a good 5 decades since then. And as a result, we have computers that are much faster, we have computers that are much cheaper, but for the purposes of the Internet of Things, they're also, for the equivalent amount of computing power, they're much smaller. They're fitting into a much, much smaller form factor. So things that once took up entire rooms came to fit into a desktop, then a laptop, a smartphone, until we get to a point where today we go to certain research labs, such as at the University of Minnesota, we have the M3, or the Michigan Micromotor, not the University of Michigan, I beg your pardon. And this is a 3D stacked chip. It's filled with sensors. It can harvest power. It has wireless communication capability. It's less than a cubic millimeter in size. And this is not as far down as we're going to be able to go by any stretch of the imagination. But it shows, as kind of a proof of concept, just how close we are to being able to put sensors literally anywhere and everywhere in our environment. The third thing that is, I think, very key to being able to make this happen at this time is connectivity. Now, early on with the internet, back in the 80s, we had Internet Protocol version 4, which allowed for addressing of little over 4 billion unique addresses throughout the internet. Now, we've been running out of space. I think a number of us know that we've moved, or starting to move over to IPv6. IPv4 was 32 bits. When they realized in the early 90s that they were going to be running out of space before long, they started working on IPv6 and decided to make it 128 bits. This change meant that instead of having 4 billion possible addresses, we now have 340 trillion potential addresses. We are going to be able to use this for quite a long time. And it's really fortunate because you've got people wanting to put a significant number of sensors out in the environment. HP has talked about their sense network, something on the order of 1 trillion sensors. Peter Diamandis, in his book Abundance, which I'm sure is here at the bookstore, talked about, I believe, in 20 years, 45 trillion sensors. So we're going to definitely need the space, but the point is that until we move from IPv4 to IPv6, we weren't going to be able to have enough unique addressable space to be able to put all of this out there into the world. So with all of this capability, what are we going to be able to do with this Internet of Things? Well, one of the things that we could do is protect our infrastructure. We have thousands, if not tens of thousands, of bridges throughout the U.S. that are in a dire state. They're near collapse or in very, very big danger of getting there. It's not possible economically or in terms of our flow of transport to take everything out all at once and just invest in all of this new infrastructure. If we take and put sensors all over all of these different bridges, as an example, we can keep track of structural deformation, metal fatigue, vibration, stress fractures, all sorts of things to be able to say, okay, this bridge has now reached a point we have to take it out of circulation. We have to work on it now before somebody gets killed. And not only save lives, but also efficiently and effectively utilize what money we do have to invest in our national infrastructure. Another place we can use it is in our natural resources. We already have sensors that look at things like stream flow and keep track of certain aspects of our environment, but we're going to be able to have so much more granular sensitivity to what all is going on. We'll be able to track stream flow, we'll be able to look at nutrient levels, pollutant levels, soil erosion, soil movement, and all of these will essentially allow us to be better stewards of our environment. And then finally, we're all looking at smart homes and that kind of thing. Well, with the Internet of Things, it's going to take smart homes quite a level up. Literally everything in your household would potentially be accessible and addressable. It can have its own sensors, it can communicate with computer programs. Perhaps your refrigerator has enough intelligence to be able to communicate with the milk cartons that are in there, or even the milk itself, to be able to know that something is reaching its past use point where it's, something's going to spoil soon. Perhaps it even has sensors that can detect certain chemicals, essentially smell that something's going off, and give you a visual notification that, hey, you need to do something about this. Or at a later point, maybe the refrigerator actually has been developed to be able to eliminate the waste, or the food from there before it goes spoiled any further. Similarly, as say certain things go below a certain level, you're getting low on milk, you've got eggs that you want to make sure that you've always got enough in stock, it goes ahead and places an automatic order for you. Somebody like Amazon Fresh comes along and delivers it to you. You've got it the next morning before you've ever actually run out of things. Saves you time, makes your life more efficient, and creates some interesting new relationships with our homes. Those are the positive things. Now let's talk about a few negative aspects. In the course of doing this, we have now all of these devices that at one level or another, even though they're maybe protected by a firewall, are exposed to the network and the internet. We've seen that over the years, we have to regularly, at least with things like Windows, patch on a regular basis in order to maintain security, eliminate security holes that are developed and found over time, and think about doing that for all of these different devices, possibly lots of different OSs, operating systems, and so forth. And there's a lot of potential for security holes throughout these a network like this. Now you may think, oh, why would anybody want to access my refrigerator? I mean, what's the big deal? Well, nothing, unless that then allows them to be able to access the rest of the network, to gain access then to, say, financial data, other personal information, and so forth. So these holes are a big potential problem in the course of developing this idea, as far as I can see looking at this. Now, there's also the aspect that when you have all of this data out there, all of these things that are coming and going into your household, there are going to be people that take interest in this. Insurance companies, as an example, might find it very, very interesting to know the rate that your household uses alcohol, tobacco, sugar, fats, and might then end up raising premiums for life insurance or preventing, even denying you coverage for stuff. There's a lot of information that's going to be out there, even if we try to take ourselves entirely off of it, because it's not like certain types of situations in the past where we can just say, well, I don't want to participate. It's going to be throughout our environment, so essentially we're all at a certain level being watched. It's not, I don't mean to make it sound like this is a paranoid perspective. It's more that when you've got this much data, and you've got big data able to analyze it, find patterns, look at any number of aspects of how we go through our world and our society, that essentially we create a very, very different world than what we're living in right now. So how small can we go? Well, in 1959, Richard Feynman, a physicist, gave a talk and wrote a paper called "There's Plenty of Room at the Bottom." And when he essentially laid out some of the early foundations of nanotechnology. K. Eric Drexler in the 1980s wrote another very important book, The Engines of Creation, which ended up really stimulating a lot of interest in nanotechnology. And we're now making some good progress. We're not as far along as we might be with biotech, and certainly as with information technology, but it's getting there. We are definitely going to be moving further and further down the scale, and it's not going to be too long, 15, 20 years, before we are definitely having prevalence of sensors, small computers, and what have you, capable of being inside of cells, in blood cells, bloodstream, what have you, in order that it might be used to help keep us healthy. It might be used to allow us extra efficiencies or even abilities, but there are also other things that we should be concerned about if we have these devices in our bodies, and I think that we will get to that point. So as we go that far down, we get down to smart dust and the idea of sensors being literally everywhere. It's not a question of thinking, oh, there's a camera over in the corner, or we've got CCTV over here. We literally have a means of being able to detect individual movement, aggregate movement, different types of behaviors within our world everywhere. And it changes, I think, the way that we will behave. Right now, you think about having privacy under certain circumstances. Do you start having more self-censorship at a point when you realize that theoretically you could always be in a surveillance situation? Not saying that anyone wants to sit around watching people 24/7 or anything like that. But when you talk about big data and the things that can be done with it, and that kind of analysis to be able to find the behavior of large populations, as you put more and more computing power out there, as you put more and more sensors out there, you gain more and more granularity, you're able to fine-tune this more and more and be able to know what smaller groups can do, what individuals will do, where somebody might be next Tuesday afternoon at 3 o'clock, or what purchasing decision you might want to make at a certain point. It might know how you will answer a particular question. These are all very important things that big data is starting to really get a handle on. And as we create all of this extra data for it to be able to work with, and the models become more and more refined, I think that it's going to create some very, very interesting repercussions for us in this world. So as we get this network established, in 2003, we had the Northeast power blackout. 55 million people were left without power. Now, this happened because some tree branches came into contact with some power lines, and there was a transient current surge. Instead of being redistributed across the power grid, it took down that little section, it shut down, and that caused additional drain on the rest of the network, and there was a cascading shutdown throughout. Now, this could be dealt with with maybe some changes to the software and the monitoring at that time. But this is one single, simple example of trying to anticipate all the different ways that a complex system can go wrong is really, well, effectively possible. So what we have to do is look at new ways of dealing with error correction, fault tolerance, having various forms of redundancy and failover to be able to deal with when our infrastructure, when different things that we absolutely depend on go wrong, that certain other things kick in to take us slack so that we don't have this kind of problem. Now, when you get really, really complex, you start to have emergent properties. And essentially, with large networks, you have something called Metcalfe's law. Now, this states that as the number of nodes, the number of connections in a network increase, that its value increases. Now, there's some dispute about exactly how accurate it is, but as far as, so long as there is effective communication and you're not introducing a huge amount of noise into the system by adding these nodes to this connectivity, it does increase value. Now, this applies to biological systems, cells, and like neurons. It applies to individuals and societies and colonies, and it applies to electronic networks as well. An example, a simple example from the biological world might be taking individual cells and how they aggregate into colonies and eventually evolve into multiform life forms, eventually simple animals onto more complex animals, eventually brains are formed, primates, and eventually we have consciousness. All of this starting off from very, very simple cells, obviously, for a long period of time. Now, I'm not saying that this vast network is going to simply wake up and become intelligent. I think that is expecting a lot. But to anthropomorphize a little bit, I do think that it will take on behaviors and priorities and motivations that aren't necessarily our own. When you have all of these different sensors and networks and systems that have their own function that they are meant to perform, and they start interacting and talking to each other and giving information back and forth, things may happen that we aren't anticipating and aren't expecting. So we have to consider these things as we move ahead. Now, just very quickly, I'm going to wrap up here shortly, but I'm just going to read from a small scenario that was part of the article. And a scenario is something that futurists use to take all of this rather dry data and often quantitative data and humanize it, make it something that is accessible and gives us a perspective of how we as people might actually experience this world. Anya's smart clock woke her gently, the time determined by her sleep phase as detected by her bed, and coordinated to her morning schedule. Despite this, as she got up, she realized something wasn't quite right. There was a mild ache in her joints, and her head felt fuzzy. Bringing up the web on her nightstand, the nearest surface at hand, Anya quickly checked Epicast and confirmed her suspicions. An H3N9 flu virus was moving through the city. Pathogen detectors had been tracking its progression for days. Fortunately, her medicine cabinet spotted the trend nearly 36 hours ago and ordered the genetically targeted medicine for that exact flu bug. It had been delivered last night and was waiting for Anya downstairs. She swallowed 2 tablets and got ready for work, knowing she'd be feeling her normally healthy self again before she left the house. On the way to the office, Anya's self-driving Prius navigated traffic as she reviewed a report in preparation for her first meeting. The cars around her maintained tight formation while speeding along at over 100 miles per hour. Lightning-fast response times combined with car-to-car to road communication allowed for capacities and speeds far greater than in the dangerous old days when people drove themselves. It was difficult to believe that at the turn of the century, traffic accidents and fatalities were hundreds of times more frequent than they were today. Nevertheless, she noted her normally smooth commute was a few minutes slower than usual. Checking the navigation monitor, she saw why. Traffic was being routed away from the old crosstown bridge. Earlier that morning, sensors had determined that stress deformation in the structure had finally exceeded federal standards. Well, better a few extra minutes in traffic than to be caught on a collapsing bridge. At the last minute, Anya decided to make a quick detour to pick up some office treats from the new 3D gastro-print chocolatier everyone had been raving about. Anyone could print their food these days, but these people were artisans. She paid for the confections with a swipe of her index finger, a minuscule chip embedded beneath her skin, effortlessly debiting her bank account. 9 minutes later, Anya arrived at her office building. As she passed through the scanners and checkpoints, she was quietly taken aside for secondary questioning. Obviously, her detour had fallen enough outside her typical routine to trip one of the security algorithms. It was an inconvenience, but given the amount of crime and terrorist activity in the world, it seemed like a small price to pay. Wasn't it? Now, this brings up some interesting things, some interesting ideas as far as I'm concerned. Philosophers have debated and talked about free will and determinism for thousands of years, at least back to Socrates' time. And I'm not a big fan of determinism. It's the idea that from an initial state, if you know enough about that system, whether it's the Big Bang or something else, if you have enough processing power, you can predict where every atom or every aspect of that system will be anywhere in the future. I don't hold to it, but some people do, and certainly some people are still writing papers about it. My thinking is, well, wouldn't it be ironic if, after all of this time, if we've had free will all of these years, that we are finally reaching a point in terms of our technological development when we end up stripping it from ourselves through the analysis, the capabilities of big data, and all of this granular, sensitive detection of movement and other behaviors. I think it could be a really, really, not necessarily the world we want to live in if we're not careful. So with that, I want to thank you for coming and listening. I really appreciate being able to share some of these ideas with you, and I really appreciate Ada's Books for making this possible, and I hope that everyone will remember to support their friendly neighborhood bookstore. So I'll take any questions if anybody has any. Thank you.
Who do you see in the next decade being the governing body for these, best practices and security measures, and do you think they will succeed?
The question is, who do I see being the governing body and regulatory power to oversee all of this in the coming years, decades, etc.? That's a little difficult to say. I think that regulation is always a really difficult area to deal with, especially at the early stages of developing technology. There can be, depending on people's viewpoints, a tendency to want to have a knee-jerk reaction to certain types of things that are new, that are changed, and to respond with sometimes rather significant draconian types of regulation. The downsides to this are that, one, we end up driving that technology underground, and we then don't get to not very feasible to think that you're going to stop any technology. Kevin Kelly wrote a really good book. If anybody wants to pick it up, I'm sure it's here. What Technology Wants, in which he talks about just this tendency that any given technology is going to come about at its given time when everything else is in place. And you can do everything you want to try to stop it. You may stop a particular individual, you may need to stop a particular country or government from making something happen. But it will pop up somewhere eventually. Now, the other thing that is a real downside, over-regulating, and I know I'm sort of sidetracking, sidestepping, I'll come back to full question in just a second. The other problem with over-regulating, or to try to opt out, and this goes back to the personal idea of opting out of staying off of the grid in your home, but it also goes with a country trying to shut things down too much, is that when you embargo at that level, you are essentially putting yourself at a competitive disadvantage. You are losing out at a very, very opportune time, and somebody else is going to eventually eat your lunch as a result. And so we have to be careful about over-regulation. Now, as far as seeing who is the body, if it's going to be a full international body, I can't see how that could happen. I would think that some of this is going to be happening or coming about through grassroots behavior and level, and some of it will be imposed through government regulation as it develops and as the understanding and the political mechanisms catch up with the advancing technology, which is usually a fairly common progression. But I think that at a grassroots level, something that I kind of mentioned very briefly in the article, and I think is definitely a consideration, not necessarily a successful one, is that in terms of all of this big data and trying to maybe deal with its predictive capabilities, I can definitely see the equivalent of like flash mobs and types of behavior by individuals or groups to effectively try to pollute this data, to be able to generate things that will throw it off in one way or another, either temporarily or in the longer term. And to that, I would think that because there's money involved at the commercial level, that the businesses and people behind the models will simply write things to be able to allow for and filter out those types of anomalies, outliers, etc., and get the data effectively to them.
Thank you.
You're welcome. Anybody else? That's fine. Yes, ma'am.
Do you have any thoughts on how the scenarios you're describing are going to affect communities and human relations?
Well, I kind of, as I mentioned, I think that some of it could be very kind of chilling on human relationships. I think that when you look at what too much surveillance has done at certain other times in our history, at certain times, for instance, some of the bad times in the 20th century, I just think that it can, if people are always concerned and never can open up to anyone because they're worried that somebody might be aware of something or find out something, yeah, that's scary stuff. And there's this idea, there's this idea that metadata is essentially anonymizes the information well enough that it protects individuals. The problem is there have been a number of papers that have been done that indicate that it only takes a few different pieces of anonymized data to be able to hone in very quickly on the actual individual. If one single piece isn't going to do it, but take 3 or 4 pieces, and then all of a sudden you've got some pretty good idea of who it was. An example I think I remember seeing was the idea that somebody anonymous surfs the web for WebMD to look at something about cancer. And The same, in a similar time frame, also in that same area, somebody buys a book about a particular type of cancer, and maybe a couple of phone calls are made to a particular doctor, and all of a sudden somebody is denied health insurance or doesn't get a job or something because of the perceived risk that's been determined because a few pieces of supposedly anonymous data come together to give somebody enough information to figure out that it's probably that person. So I'm not sure if that answers your question, but okay. Another question like that?
Yeah, I thought the idea of having sensors, like your example of bridges and in natural systems, like that seems very interesting. And like by Moore's law, we have the power to put smaller and smaller and more powerful computers everywhere. But what about the sensors themselves? Like what kind of sensors are we looking at, and are they kind of decreasing in cost in the same way?
The trend in terms of all of this, micro machines, small computer chips, they are definitely shrinking. And you're able, I can't tell you the exact form. I do know that M3, for example, from Michigan, does include several different types of sensors. I can't remember off the top of my head what all they do, but if you've got a particular sensor that can, or a particular device that can, let's say, sense 3 or 4 different things, then you can probably reprogram any number of them, just put them out into the environment, and depending on where they are, literally, in the case of smartphones, where they land, rather than having to specifically place anything, they may be able to be self-programming to specify, okay, I need to be, I'm this close to these other sensors that are doing this job, I'm going to do this. I can't tell you the specifics of how this will develop, but you can foresee some definite possibilities. Yes?
Well, one of the major things you said was driving this is going to IP version 6. So do you see other standards bodies being a contributor to how this is going to wind up being? I mean, because those things are sort of driven from a business perspective, and the different manufacturers getting together and finally deciding on a commonality between interfaces.
There are some standards that are being worked on. I have heard in terms of not so much operating system, but intercommunication and programming. And I can't really put my finger on anyone as a specific name at this point, but yes, exactly. There has to be continuing growth and development of industry standards in order for this to all come together. To my mind, one of the big concerns and problems is when you start having disparate systems talking to each other. There's all kinds of ways that can go wrong in terms of that interaction. And so we need to have as standardized a method of bringing all these together as possible. And I think we're still very much a kind of a wild west of figuring out where that's going to be at this point. Yes.
So die sizes have been shrinking with Moore's law, but how has sensor sizes gone down? Because you can't have a smaller atom or smaller photon. They're keeping the same. But how is that relating to sensor size?
Okay. Sensors can be etched in a similar way. Now you can't go to certain atom sizes in terms of either one really until there's potential ways to compute beyond that, I suppose. But really, yes, there are going to be limits both in terms of electronic scale, but also for mechanical scale as well. there is a bottom. But exactly where that is and how far is, we've got to yet to see. We're approaching nanotechnology really from both a bottom-up and a top-down type of approach at this point. And it'll come together, but we're still a ways away from being able to really get really very, very, very small sensors, but they will come about. And one other thing within nanotechnology is the trend to move toward mechanical analogs, correlates, to what we do electronically with computers. Instead of it's almost a little bit like going back to Babbage in terms of using a mechanical method of switching and so forth. So, all right. Well, thank you very much all for coming, and enjoy the rest of the afternoon. Thank you.
As a futurist, do you have any fiction recommendations? Are there any fiction authors?
Oh.